set. We're here to do some quantum entertainment. We're going to do the overview. The things that I just wanted to convey real quick is I appreciate everyone coming today. Cliff and I have been, really thinking about what's the right way to engage our industry in this idea. And, are we too early? Are we not early enough? A lot of these questions have come up, but hopefully today we'll have a dialogue, we'll have some presentations, and some of these ideas maybe will come clear into focus for all of us, and we'll kind of see where we need to go from here. But without further ado, I'm Bijan Nowroozi.
Put the mic a little closer, yeah.
Yeah, I'm Bijan Nowroozi. I'm CTO here at OCP. I'm very glad to meet your acquaintance.
And I'm Cliff Grossner, and I'm the Chief Innovation Officer, and been working with lots of you folks to understand what we want to talk about this afternoon and help the OCP audience learn a little bit about quantum and why they should care about it. And for that, I think Bijan and I prepared just one slide to share with people. There it is, about what we see as the next disruption. So currently, we've been working on introducing and making the GPU an integral part of the data center. That is for AI. And we won't talk about where neuromorphic computing fits in somewhere in this GPU phase of neuromorphic computing. But ultimately, we believe that for computation, quantum is the next adjunct that will be added to the data center, and we're already seeing that in some of the high performance computing installations in the world, right? And we see a parallel track for communications where we had electrical, we're going to optical or photonic now, and we're kind of riding the photonic wave, right, as Bijan's been telling me, and going to quantum on the communication side as well. And to kick off the session, we have two university professors, if I've got that right, so to help us get started on our education around quantum. And I think the first speaker is Yasser, right? So Yasser, why don't you come on up? And you've got about 12 minutes to, and we'll watch for you. So we'll warn you.
Okay. So hello everybody. Thank you very much for the kind invitation and congratulations on this initiative. I wasn't aware. This is very interesting, and I'm already learning a lot. So yes, so I'm Yasser. I'm a theoretical physicist, but I'm a nice guy, and I want to tell you a bit about quantum computation. So to introduce this session. So a quantum computer is a machine that processes quantum information. This would be my definition. And quantum information is really a new paradigm of information. This is an interesting, deep point that one could discuss, but now being practical, it's about harnessing the properties of quantum physics, meaning the physics that allows us to understand and describe and control nature at the atomic scale and subatomic scale, to develop new information technologies, in particular new information processing technologies, the quantum computer. And so these are the quantum superposition, the quantum entanglement, so types of states that can only be harnessed at the quantum scale. And this offers us a sort of natural parallelism without the need for more than one processor. And so there's this expectation that quantum machines based on the laws of quantum physics could process information much, much faster than we currently have. Another aspect that is now emerging that I think is extremely interesting, although I'm biased because I do research on that topic as well, is the potential for energy advantage, for having more energy efficient computers harnessing these laws of quantum mechanics. So what are the challenges to actually have quantum computers? We do have quantum computers, but they are essentially prototypes, early machines, still not fully developed, but they are indeed already being installed in classical supercomputing centers. So I cannot really read there, but so I can read here. It's okay. I think it's good. So what are the challenges? So first is how to scale. We have prototypes with dozens and dozens of qubits, but we need machines with, thousands or millions of quantum bits. How to scale? There's many challenges there. This is the main challenge to having a quantum computer overall. And there's different platforms one can consider. So at this stage, we don't know if the future quantum computer will be based on atoms or ions or superconducting currents or photons, or that would be great based on semiconductors, because we have the whole industry and foundries, etc., already from the classical computing industry. So it's still at an early stage, and maybe some other technology will emerge, or maybe more than one will work, but we're still at that early stage exploring the different paths. The next one is how to network quantum computers. And this question makes sense both at local distance and long distance. So long distance, we are now, as a community of scientists and technologists and industry, developing a quantum internet. So for example, in Europe, there's a project devoted to that, in the USA as well, and I guess in other places in the world. But to have a quantum local area network, to manage to connect the quantum processors in a quantum way, with quantum leaks, with quantum correlations, could be, and maybe is the most promising strategy to scale, because we're finding limitations in terms of growing the chips. The other challenge is, what can we do with these quantum computers? In which problems can we expect a significant speed up? And so, famous problems for quantum computers are problems based on quantum physics or quantum chemistry, both scientific or industrial applications, say for pharmacy, material science, etc. But then there's many optimization problems, geometric data, machine learning, cryptanalysis, etc. But in fact, we don't have that many quantum algorithms with a speed up, right? So I put there your name here, because, paraphrasing the Monty Python, every speed up is sacred. It's hard to find. And so there's a lot of research is necessary. There's a lot of investment on developing the hardware, on scaling the hardware, as it should be, but we need a lot more use cases and algorithms, right? So Hartmut Neven, leading the Quantum AI Lab, famously said in an interview a few years ago, my biggest nightmare is waking up tomorrow having the quantum computer ready, fully scalable. What do I do with it, okay? So this is a challenge to address. So just want to tell you that a network of research institutions across 6 European countries, we created the European Quantum Software Institute. We try to have some events online, etc., to try and promote this agenda. We need more fundamental results on the algorithmic side, on the scientific, theoretical computer science side. Then there's also the challenge of how to hybridize quantum and classical machines. I'll come back to that. And then many challenges, how to deploy these machines, including the hybrid approach, how to integrate them, how to, what middleware do we need, how to manage the access, the business cases, the standards. And throughout this very interesting session today, we'll have very nice speakers addressing these questions so that we can learn and discuss about them. And then could we have energetic advantage? I'll briefly mention that at the end. So let me focus here on the hybrid quantum classical, because I think many people here are from the classical computing background. And I think I forgot to, You're good. Okay. And this is actually now, so in Europe, the European Commission started a program. They deployed already 6 or 7, depending how you count. So 1 plus 6, or they are in the process of deploying 6 quantum processors in 6 HPC centers, and there's already a program to have more. And so this is now becoming a very hot topic, hybrid quantum classical computing. And the hardware is advancing, the installation, integration is progressing, but what to do with these machines and how? As a scientist, we haven't found many answers. So I wanted to put this also as a challenge for us as a community to discuss. And so why and how to hybridize quantum and classical computers? Is it because our quantum processors are limited and we want to do some stuff with them, so we need to get some aid from the classical processors, given the limitations of the current quantum processors? Another motivation is, could this become an accelerator? So the idea of the QPU, the quantum processing unit, as an accelerator to the classical machine, akin to the GPU. So that's, of course, a very good motivation. But how to actually do that? For which applications? Where does this make sense? How do the hybrid algorithms perform? Okay, so far we essentially have variational methods, for those who know them. These are empirical methods. We cannot really benchmark that well. Of course, we would be able to benchmark in seconds if we had, big hardware, but now it's very, very much just, testing some proof of principle. So but from the theoretical computer science point of view, we don't really know how this performs in the cases where they are not variational, and we could have, do the proper complexity theory. So we are starting to do this in a European project called just hybrid quantum classical computing, and how to implement this. And so I just want to tell you about some research we're doing addressing this question. So We want to implement a quantum algorithm. The quantum hardware is still not good enough, doesn't keep the quantum coherence, the quantum regime for long enough. So are there strategies to address this? And so we've developed two methods. We just call them parallelization and interpolation. It's an intuitive name. So, and it looks very intuitive, but we were able to do the proper mathematical proof. So, I have a problem. It's my quantum processor cannot handle it, doesn't have enough coherence, enough circuit depth. So what I can do is I can partition the input and use small chunks of the input in the same quantum processor, and then measure and combine these classically. So that's one way of hybridizing. And then the opposite, I keep the input, but I make the processing unit a bit smaller, a bit simpler, and then I can also find a way to combine the individual results and get the result I want. This is a theoretical result based on an approach on query complexity, which is maybe not so practical in terms of really giving practical solutions, but is the framework that allows us to get formal proofs, and so then we can understand really the advantage and measure, have scaling formulas, etc. Understand, because there's an intuition, but there's still very little scientific or practical results telling us how to hybridize and exactly what advantage I get from that or not. So there's still a lot of research needed. So finally, to conclude, can we have an energetic advantage? I want to show you this result by my student Francisca and my postdoc Marco. So we tried to, we studied how to implement a quantum Fourier transform, so the quantum version of the classical discrete Fourier transform, in a quantum processor based on trapped ions with 7 qubits from the group of Christoph Wunderlich in Siegen. For the first time in a previous collaboration and paper, we measured how much energy it takes, all the steps of the quantum their quantum processor. And so from those measurements, which we published in a different paper, we were able to extrapolate the energy cost of implementing a quantum Fourier transform. And you see that the blue, this is the number of qubits in the bottom, and this is the energy in joule. And the blue is our estimate of how much energy we would need to implement this quantum Fourier transform. And you see it scales very nicely. And in red and yellow, you cannot really distinguish. We looked at what, according to the best of our knowledge, are the best classical supercomputers, both in terms of time and energy performance. And you see that things seem to scale much better at the quantum level. So this is a first indicator that is very exciting. This is a simple scenario. His trapped ions process only have 7 qubits. That's why you see these chunks of 7 blue dots. So we'd have to see how to network this or how to scale this, how to make error correction that we are not doing here. But still, it's a very exciting result that we just put in the archive a few days ago, actually. And this is it. So call to action. What do we need for quantum computer? Well, we need better scalable quantum hardware. More qubits, but better quality. Including developing quantum random access memory. So there's a lot of effort on the hardware that is still necessary. We need solutions to exploit the networked quantum processors, especially at the local area. So this could be a solution to scale the machines that are limited in scalability. We need much more quantum algorithms, much quantum software with applications that really there is quantum speedup, including strategies and methods to harness these hybrid quantum classical computers. Now, a hot topic, I think it deserves to be a hot topic, but I see many people talking about it just, we bring the machines and the miracle happens. We need a lot of understanding to exploit that. More quantum middleware standards and integration solutions. We'll hear also more about that. We need to manage expectations. I think we are in a quantum hype, and this is not good, okay? And I think overall in the academic community, I've witnessed the same in North America, we are concerned about this hype. This is super exciting. To me, this is a revolution. This is a scientific and technological revolution. It's a new type of information in the information society that we live in. Something will change, but we should be, moderate expectations. And then finally, an invitation to consider and explore novel directions that are still not sufficiently considered. For example, the potential quantum advantage in energy consumption. It may turn out, I don't know, that the biggest advantage of quantum computers is the energy efficiency rather than the speedups. Thank you very much.